suppose that we got a structure. So this is our structure, okay, lying on the ground. So this is the ground level, and we know that earthquake is nothing but the lateral load. So just like the wind load that acts in the horizontal direction, not in the vertical direction, earthquake also acts in the horizontal direction. That is why it is known as the lateral load. So suppose that a lateral load is acting of 5 kilonewton in this structure. In that case, the structure will give a reaction at the base, or that is on the ground, of 5 kilonewton in the opposite direction. So if it is acting in the x direction, it will act in the negative x direction. Now, by doing this, the structure will be stable. So if we increase the load to, suppose, let's say 15 kilonewton, the structure will give back the reaction on the ground 15 kilonewton. If we keep on increasing the this lateral load value, this reaction value will also keep on increasing. But can this load value keep on increasing? No, the building has got a certain limit, and this value will increase only up to that limit, and it will not increase beyond that limit. Suppose that the maximum capacity of this building to give this reaction is only, let's say it's 100 kilonewton. So it cannot give this reaction of 100 kilonewton, more than 100 kilonewton. In that case, if you apply the load of 101, or let's say 105 kilonewton in this direction, the structure will collapse. So this maximum reaction force, or you can say the force that occurs at the base of this structure due to the lateral load, or you can say the ground motion that occurs during the earthquake, this maximum force is known as the base shear. What it is called? Base shear. So you must have heard this word, base shear. So this is nothing but the maximum lateral force, or the maximum reaction force that occurs at the base of the building due to the ground motion during the earthquake, or the lateral load due to the earthquake. Base shear is the maximum force. Okay. So when we design a building, you can see that a building can give the reaction from 0 kilonewton up to the base shear value. So we do not design for any intermediate value, and we design the building for the base shear. So we make the building such that it can take the lateral load, or the load due to the earthquake, that is equal to the base shear of that building. I hope you understand this concept. So now we need to know the base shear of any building that we are designing, so that we can design that building for that much of lateral load. To do this, we need to calculate the base shear. Okay, so how we can do that? So this can be done using a code, or there are lots of code, but the code that I'll be explaining here is IS 1893 2002, and the latest revision is 2016. So there are other codes such as UBC code. They are pretty much similar, only in basic difference. And if you understand one code, and you can obviously understand the other codes, you need to refer the code that is followed in your country. So in my country, this code is followed. That is why I'll be using the code here, and you can follow along with the code that is adopted in your country. The basic concept for the calculation is pretty much similar, and you won't have much problem. So now let us see how, as per IS 1893 2002, we can calculate this base shear. Okay, so you can see here design lateral force. This is IS 1893 2016, and the clause is 7.2. So you can download this file from this video. So design lateral force: building shall be designed for the design lateral force VV, that is the base shear, given by VV is equal to AH into W. So this code has given the formula to calculate the base shear. The formula to calculate the base shear VV is equal to AH times W. So now we need to understand what AH is and what W is. So let me just say what W is. So W is the seismic weight of the building. So seismic weight of the building. Okay. And how do you calculate the seismic weight? In a building, if this is our building, we got different floors. All right. So we got floors. We got floors: first floor, second floor, third floor, and fourth floor. And here we got different structural members. We got beams, we got columns, we got floor. So on a floor, we got beams, slabs, and we got columns. So we can calculate the dead weight of these structural members. So that is the dead load. And on this floor, we got various items, such as it can be a bed, it can be table, it can be anything, other things that are found generally in a house. Those things are called as the live load. So we add dead load plus live load, and using this load we get the floor load. For this floor we get load. For this floor we also do the same thing. For this floor we also do the same thing, and we get floor load 1, floor load 2, floor load 3, and floor load 4. And if we add all these floor loads, we get the seismic weight of the building. And here the dead load is whatever the load we get by using the formula gamma times the volume. Gamma is the unit weight, V is the volume of that structural members. We use the 100% of that load. And for live load, we reduce the live load because during the earthquake, not all the people are inside the building for which we design it normally. So what is this factor? We'll see that in a while. So here I just want to give you a concept. Okay. So we know the seismic weight of the building and we can calculate it. The software will do that for you as well. And if you want to do that manually, you can do it. Okay. Just calculate the dead load of all the structural members and calculate the live load on all the floors and add them. And live load you have to multiply with certain factors. So we know W. Now we need to know the AH. So AH is called as the acceleration coefficient spectrum. We know that earthquake is not same everywhere. So it might be severe somewhere. So earthquake effect of the earthquake is not same on all the soil types. So it is different in the rocky soil. It is different in the loamy soil, and it is different in the soft soil. Also, the behavior of the earthquake is different as per the building type. So on the masonry buildings, it acts differently. On the RCC buildings, it acts differently. We have to take all these things, the location, type of the building, okay, so building, type of the building into account while calculating the base shear. These all things are given by AH. Now let us see how we can calculate AH. So if we go to the clause, so it's on up. Okay, it's somewhere here. So if we go to clause 6.4 of IS 1893 part 1 2016, you can give the formula to calculate AH. So design horizontal seismic coefficient AH for a structure shall be determined by, so AH is equal to Z by 2 SA by G. So let me write this. So AH we gave as, so if you see, it's Z by 2, here SA by G, and it's R by I. Okay, so here Z is the zone factor. Z is the zone factor, you can see in the IS code. And how do we calculate this? We'll see this in a while. So SA by G is design acceleration coefficient. So it will talk about the kind of the soil. It will talk about the location of the building. And R is the response reduction factor. So it will talk about the type of the building. So it is whether it is a brick wall RCC. So if it's a RCC, what kind of RCC it is, whether it is a steel structure. Okay, so type of the building, and I is the importance factor. Importance factor. So it will also talk about the kind of the building. So I must say, kind of the building. If in the building there is a lot of movement of the people, then that building is very much important. And if in the building there is not much movement of people, in that case that is a less important building, we can say. Okay, now let us see one by one how we get the extract these information from the code. So let's talk about the zone factor first. So zone factor, that is Z. And if we see the code, and we can see that so let's go down. Okay, so if you see table 3 of the code, and you can see the zone factor, and if your building is located in zone 2, the factor is 0.10, and if your building is located in zone 3, factor is 0.16, and if your building is located in zone 4, it is 0.24, and if your building is located in zone 5, the factor is 0.36. Okay, and so I live in Kathmandu, so Kathmandu, Nepal. So this our entire Nepal is located in zone 5. Because it is seismically very active area because of the collision of Tibetan and the Indian plate, and due to which the seismic activity is a lot in our area. So zone 5 is the highly seismically active zone. So high seismic zone. Okay, and seismic zone, and a great care needs to be taken while designing a seismic resistant building in this area. The value for Z for Nepal is 0.36, and if you live in other places, you can find the zone using the map of India. So if you live in India, okay, so we got a map here. So this is the map of India. So a lot of zones have been demarcated here, and you can find your respective zone. So this is Nepal, and this is entire zone 5. Okay, entire zone 5. So next thing we need to know is the SA by G. So SA by G. So SA by G. Okay, so the code tells us how we calculate SA by G. So here it says it. Okay, so design acceleration coefficient. So here it says it shall be taken as that corresponding to 5% damping. So we assume in a building 5% damping ratio, and for that 5% damping ratio, SA by G values are given. So for use in an equivalent static method, for use in response spectrum method. So equivalent static method and response spectrum method are the two methods by which you can apply the seismic load. So the method that we are using now is the equivalent static method, because here what we do is that, I'll just tell briefly here. We'll just calculate the base shear VB. So I'm going into this. Okay, so let us suppose that we calculate it. So this is this force that acts at the base of the building. Now what we'll do, we'll distribute this base shear into all these floors. Okay, suppose that if this load is 100 kilonewton, and there is a formula to distribute this 100 kilonewton in all the floors, and we'll use that, and only this much of load will be applied in this building. There won't be greater load or lesser load than this value. So due to this reason, this method is known as the equivalent static method, because the loads are static. But in the dynamic method, what we do is that we apply the load as a function of time. Earthquake load is also a function of time, and so here also we apply the load as a function of time, due to which more accurate results are obtained. So right now, as we are doing the equivalent static method, and later we'll see the response spectrum method as well. So here SA by G for rocky or hard soil sites. So this information you get from your geological data or geotech study that you do at the site. Okay, and here it says it's 2.5 if the time period of the building lies between 0 to 0.40 seconds, 1 by t if the time period lies between 0.40 second to 0.4 second, and 0.25 if the time period is 4 second. Similarly for the medium soil and also for the soft soil. Now to calculate SA by G, we need the time period of the building. So how do you calculate the time period? For that also the formula is given. So let us go down. And let us go to the, okay, so this is the, okay, not now, not here. Yeah. So here the time period, the formula for the time period is given in clause 7.6.2. And so the design base shear VV along the principal direction of a building is determined by VVAH into W. So I just talked about it. The approximate fundamental translation natural period TA of oscillation in second shall be estimated by the following expressions. So bare MRF buildings means that the buildings without masonry infills, so without the brick walls. So if you got a building that doesn't have any brick wall, in that case you use this formula. So TA is 0.07 into height. H is the height of the building from the ground to the top, to the power 0.75. If it's a RC MRF building, so RC means reinforced concrete MRF building. So MRF is movement resisting frame building. Okay, so if it's a RC and steel, you use this formula. For steel only, you use this formula. And for the buildings with RC structural walls, that means for the buildings with a shear wall, you use this formula. And here comes our formula, that is all other buildings, which is our building as well, because it has got a masonry wall and it is a RC MRF building. So we use this formula. Time period TA is equal to 0.09 times root over D. So time period is, the expression for the time period is T is equal to 0.09 upon root over D into H. So where H is the height of the building and D is the base dimension of the building at the plinth level, which means that if this is our building, okay, so let me draw this. If this is our building from the ground floor to the top of the building, so this is the height, and if this is the plan of the building at the ground floor level, so this is X direction, this is Z direction, so this is X, this is Z. So this is known as dx, so that is the base dimension in the X direction, and this is known as dz. If your building is square, it can be same in both the directions. Okay, so using this formula you can find the time period of your structure, and from this time period what you can do, you can find SA by G. We know Z, we know SA by G. Next thing that we want to know is the R, that is the response reduction factor. When the building is subjected to the earthquake motion, so how well it absorbs this earthquake force is the idea of response reduction factor. So to calculate response reduction factor, again we go to the code and let us see where it is given. Not here, okay, yeah, over here. Table 9 will give you the idea. So response reduction factor R for building, so lateral load resisting system, and the R, so movement frame systems. So our buildings are movement frame systems. So RC buildings with ordinary movement resisting frame, that is OMRF buildings. So these OMRF buildings are those buildings so which has been designed using the design code, that is for India it's IS 456, but they haven't been detailed using the detailing code, that is IS 13920. So they haven't been ductile detail. Okay, they have been designed as per the code but not ductile detail. So next is the SMRF. So SMRF buildings are those buildings that have been designed as per IS 456 and also ductile detail as per IS 13920. So similarly we got for the steel buildings as well. So our building is this building. So the response reduction factor is 5.0, that is 5. So we know the response reduction factor as well. Next is the importance factor, and let us see how we calculate it. Okay, where is the importance factor? Okay, so damping ratio, let me shortly talk about it. So damping ratio means that how well the vibrations in the building goes into damping, or disappear in the structure. So we take the damping ratio as 5%. So as I've already told, importance factor will talk about how important the building is. So importance factor I. So here you can see that important service and community buildings or structures, for example, critical governance buildings, this and those buildings where the live load is very much high, give the importance factor as 1.5. And for residential or commercial buildings, give the importance factor as 1.2. And all other minor buildings give the importance factor as 1.0. Okay, so importance factor is different as per IS 2002. So in IS 2002, if the building was important, it was 1.5. For all other buildings, it was 1.0. So this is 2016, a bit enhanced form of IS 2002. So here the note has been given that owners and design engineers of buildings or structures may choose value of importance factor I more than those mentioned above. So you have got all the liberty to choose the importance factor more than these values. Okay, for example, you are building your own house or building a house of any person, and you consider that this person is very important. Maybe it's your family and you take them very important, and in that case you may think that 1.2 is not sufficient. I'll take 1.5 with 1.5 factor. So it will give more strength to your structure, but it will make your structure a bit more expensive as well. Okay, so we know the importance factor as well, and we know all these things. So in using these all values, we can find AH, and using AH we can find VV, base shear, and using the base shear we can apply the load in various floors of the structure. So how we do that? So there is another calculation. Now I assume that we know how to find the base shear. Okay, so let us talk about the percentage of imposed load to be considered in calculation of the seismic weight. So if the live load intensity is less than or equal to 3 kilonewton per meter square, then you have to reduce the live load to 25%. Okay, and if it is above 3.0, you have to reduce it to the 50%. And for the roof, imposed load on the roof, you don't have to consider, because during earthquake we don't assume that there are people on the roof. So now as per clause 7.6.3 of IS 1893, the design base shear VV computed in the 7.6.1, that the design base shear we just saw, shall be distributed along the height of the building and in plan with each floor level as below. So vertical distribution of the base shear to different floor levels. So as I told you that we have to distribute the base shear to different floors. So design base shear VB computed in 7.6.1 shall be distributed along the height of the building as per the following expression. So using this formula, you have to distribute the base shear. So okay, so please check this formula in the code. Okay, so I cannot explain this right now in detail. Alright guys, so this is how the earthquake load is calculated and applied in STAAD Pro using IS 1893, you can say 2002 or 2016. And now let us see in STAAD Pro how we actually do it. Dynamic analysis methods. Earlier in IS 1893 2002, we could only do the equivalent static method of earthquake analysis. So that was sufficient for the buildings, for the normal buildings. Okay, but as per IS 1893 2016, equivalent static analysis method is only applicable in the buildings that are lower than 15 meter height and that lie in zone 2. So you can do equivalent static method for such buildings that are located in zone 2 and having height less than 15 meter. But for all the buildings that are located in other zones, So if in zone 5 a building of 3 meter or single story building exists, you have to do the dynamic analysis method. So linear dynamic analysis shall be performed to obtain the design lateral force, design seismic base shear and its distribution to the different levels along the height of the building. So you have to calculate the design base shear that we just talked right now, and after that you have to distribute it to the different floor levels along the height of the building and to various lateral load resisting elements for all buildings other than regular buildings. So we have to do this dynamic analysis for all the buildings, and it is not necessary in the buildings other than regular buildings that are lower than 15 meter in the seismic zone 2. So how do we do the dynamic analysis? So there are two methods. One is time history method and another is the response spectrum method. And we will see these two methods.